आपण काही ऑर्गॅनिक कंपाऊंडचं ऑप्टिकल आयसोमरिझम स्टडी करणार आहोत आणि थोडंसं डिटेल डिस्कशन आपल्याला करायचं आहे. तर ऑप्टिकल आयसोमरिझम स्टडी करत असताना आपण काय बघणार आहोत? वी हॅव टू स्टडी इज इट हॅव्हिंग कायरल कार्बन. फर्स्ट आपला पहिलं त्या ठिकाणी व्ह्यू काय असणार आहे? इज इट हॅव्हिंग कायरल कार्बन, त्या मॉलिक्यूलमध्ये कायरल कार्बन आहे का? देन नंबर ऑफ पॉसिबल स्टेरिओआयसोमर्स फॉर दॅट कंपाऊंड, आणि मग त्या स्टेरिओआयसोमर मध्ये असणारं रिलेशन आपल्याला स्टडी करायचं आहे. नाउ लेट अस सी ऑप्टिकल आयसोमरिझम इन सिलेक्टेड ऑर्गॅनिक केमिस्ट्री. लेट अस सी अ सिंपल एक्झाम्पल ऑफ लॅक्टिक ऍसिड. यामध्ये पहिल्यांदा एक्झाम्पल आपण घेऊया लॅक्टिक ऍसिड या कंपाऊंडचं. ओके, दिस इज द फॉर्म्युला फॉर लॅक्टिक ऍसिड, CH3 CHOH and COOH. Now to study the optical isomerism, we first know about the chiral carbons present in that molecule. Is it having asymmetric carbon atom? Is it having chiral carbon? हे आपण पहिल्यांदा बघतो आहोत. Now what's about the lactic acid? That methyl group, is it chiral in nature? It is attached to the 3 hydrogen atom. Means it is attached to the same atom or group, hence it is not chiral. But that second carbon, which is marked by star, it is attached to the 4 different atoms or group. OH is the first one, methyl is the second one, that hydrogen is the third, and that COOH is the fourth. Means that carbon is attached to the 4 different atoms or group, and hence it is chiral in nature. And thus that lactic acid having 1 chiral carbon. Now we know that according to formula 2 raised to n, we can calculate number of possible stereoisomer, where n is number of chiral carbon. Now putting the value in that formula 2 raised to 1 is equal to 2, means lactic acid should have 2 possible stereoisomer. Lactic acid should have 2 possible stereoisomer. Suppose this is the first stereoisomer. Okay, this is the first stereoisomer. In that stereoisomer, I have shown the arrangement of atoms or group around the chiral carbon. आपण या कायरल कार्बन भोवती ऍटम किंवा ग्रुपची रचना दाखवलेली आहे. दॅट कार्बन इज अटॅच्ड टू द OH, हायड्रोजन, COOH and CH3. This is the first stereoisomer, while this one is the second isomer. In first case, we have shown that OH group at the right hand side, while in the second case, that OH group is shown at the left hand side. Means in that 2 stereoisomer, arrangement of atoms or group around the chiral carbon is different. Now we know that both the stereoisomer, they contain chiral carbon, and also there is no element of symmetry. They do not having any element of symmetry, and therefore they are optically active. They shows optical activity. Why they are optically active? Because there is a chiral carbon, there is no any element of symmetry, hence they are optically active. Okay, what is the relation between that 2 optically active compound? What is the relation between that 2 optical isomer? Suppose this is the mirror in between them. Then one isomer looks mirror image of another. One isomer looks mirror image of another. आणि यामध्ये एक इमेज आपण उचललं आणि दुसऱ्यावरती मॅच करायचा प्रयत्न केला. They do not match with each other. They do not match with each other. ओके, म्हणजे इथं जो हायड्रोजन आहे त्यावरती OH येईल, इथं जो OH आहे त्यावरती इकडचा हायड्रोजन येईल. मीन्स दे डू नॉट मॅच विथ इच अदर, अँड देअरफॉर दे आर नॉन सुपरइम्पोजेबल मिरर इमेजेस ऑफ इच अदर, अँड thus that stereoisomers of lactic acid, they are optical isomers. They are optically active and they are non-superimposable mirror images of each other, and hence they are called enantiomers. मग आपण पहिला पॉइंट ते सांगतोय. Thus these 2 are optical isomers and they are non-superimposable mirror images of each other, hence they are enantiomers. Now they are differ in their action on PPL. One can rotate the plane of PPL in a clockwise direction, it is called dextroisomer, while another can rotate the plane of PPL in anti-clockwise direction, and this is called as the L isomer किंवा आपण त्याला Leo isomer असं म्हणतो. Okay, this is the L isomer, actually Leo isomer. Okay, these are the 2 possible isomers. One is the dextro and second one is the Leo isomer. Lactic acid exists in 3 form. यामध्ये पहिला फॉर्म कोणता आहे बघा, D lactic acid, then second one is the L lactic acid, and third one is the DL lactic acid. These are the 3 main forms of the lactic acid. What is meant by D-lactic acid? It is a dextroisomer of lactic acid. This one is the D-lactic acid, dextroisomer. It rotates the plane of PPL in a clockwise direction, and its a specific rotation is the plus 2.24 degree. Means it can rotate the plane of PPL in a clockwise direction by an angle 2.24 degree. While L-lactic acid, second is the L-lactic acid, it is the Leo isomer. This is the Leo isomer, and it can rotate the plane of PPL in anti-clockwise direction. Now, what should be the alpha of L-lactic acid? Both isomer, dextro and Leo isomer, rotate the plane of PPL by the same angle, by the same angle, but in a different direction. फक्त त्यांची डायरेक्शन वेगवेगळी असेल, पण त्यांचा अँगल मात्र सेम असणार आहे. दे रोटेट द प्लेन ऑफ पीपीएल बाय द सेम अँगल, अँड देअरफॉर द स्पेसिफिक रोटेशन ऑफ एल लॅक्टिक ऍसिड लिओ आयसोमर शुड बी द सेम. फक्त त्याला आपण निगेटिव्ह साइन देतोय, कारण याला पॉझिटिव्ह म्हटलेलं आहे बिकॉज इट रोटेट द प्लेन ऑफ पीपीएल इन क्लॉकवाइज डायरेक्शन, म्हणून याला प्लस 2.24 असं म्हटलं. While the alpha specific rotation of L-lactic acid is minus 2.24 degree. Means angle is the same, just the direction is different. Therefore, we are using negative sign, minus 2.24 degree. Okay, this is the specific rotation of L-lactic acid. Then third form, यामधला तिसरा फॉर्म कोणता आहे? DL-lactic acid. DL-lactic acid means it is a racemic mixture. It is the racemic mixture, means dextroisomer and leoisomer of lactic acid. त्याला जर आपण इक्विमोलार प्रोपोर्शन मध्ये घेतलं, then it is called DL lactic acid. It is the racemic mixture, and we know that it is optically inactive. Racemic mixture is optically inactive, and therefore its a specific rotation should be 0. त्याचं स्पेसिफिक रोटेशन म्हणजे अल्फा हा 0 असला पाहिजे, बिकॉज इट डू नॉट रोटेट द प्लेन ऑफ पीपीएल टुवर्ड्स क्लॉकवाइज और अँटी क्लॉकवाइज डायरेक्शन. ओके, नाउ दिस इज जस्ट अबाउट द फर्स्ट कंपाऊंड. आपण पहिला कंपाऊंड बघितलेला आहे लॅक्टिक ऍसिड. ऍक्च्युअली पहिल्यांदा आपण ऑप्टिकल आयसोमेरिझम स्टडी करताना काय पाहिलेलं आहे? इज इट हॅव्हिंग कायरल कार्बन? Okay, yes, that molecule having one chiral carbon. Therefore, according to formula 2^n, it should have two possible stereoisomers. We have shown that two possible stereoisomers for lactic acid. मग त्यामध्ये असणारं रिलेशन आपण पाहिलं. Both the stereoisomer having chiral carbon, they do not having any element of symmetry. Hence, they are optical isomers, and they are non-superimposable mirror images of each other. Therefore, they are enantiomers. Thus, lactic acid exists in three forms: D-lactic acid, L-lactic acid, and DL-lactic acid. Okay, this is just about the first organic compound, lactic acid. Now, let us see study of second one. यामधला दुसरा कंपाऊंड आपण बघूया, ऑप्टिकल आइसोमेरिझम इन अ टार्टारिक acid. Okay, this is the structure of tartaric acid. थोडंसं स्ट्रक्चर त्याचं बघा. Tartaric acid, okay, COOH. First, there is one carboxylic group, COOH. Then CH, again OH, CH, OH, and finally there is again COOH. Okay, this one is the tartaric acid. Now, our first question, yes, is it having chiral carbon? To study the optical isomerism, we must know about the chiral carbons present in the molecule. Therefore, first point is the chiral carbon. What's about the carbon of COOH? That carbon of COOH is not chiral in nature, because it is not attached to the four different atoms or group. Hence, it is not chiral. What's about the second one? That second, suppose I will make star. That is attached to the one COOH. Second is the OH. Third is the hydrogen. And fourth, that whole group. And therefore, thus that carbon is attached to the four different atoms or group, and therefore that carbon is chiral in nature. Okay, and what's about the next carbon? Suppose I will make star here. This carbon is also attached to the four different atoms or group. तो सुद्धा चार वेगवेगळ्या atoms किंवा ग्रुपला अटॅच आहे, and hence it is also chiral in nature. Thus, tartaric acid contains two chiral carbon. Means it obeys first condition. पहिली condition तो obey करतो. There are two chiral carbon in the tartaric acid. Now let us see number of possible stereoisomer. We can calculate by the formula 2 raised to n, where n is number of chiral carbon. By putting the value 2 raised to 2 means 4. Barabar. That means that compound should have 4 possible stereoisomer. That compound should have 4 possible stereoisomer. Suppose this is the first stereoisomer. Just see the structure. Okay, this is the first one. This one is the second. Now, what is the difference between first and second? In first case, first OH is shown at the right hand side, and second OH is shown at the left hand side. While in the second one, first OH is shown at the left hand side, and second OH is shown at the right hand side. Okay, this is the second isomer. This is the second isomer. Okay, just we have shown the different arrangement of atoms or group around the chiral carbon. Okay, this is the third one. Here we have shown both the OH group at the same side. They are shown at the same side. While let us see one more possible stereoisomer, fourth one. Here that both the OH are shown at the same side, but they are present at the left hand side. While in the third, both the OH are shown at the right hand side. Okay, thus there are 4 possible stereoisomer for tartaric acid, and these are the 4 possible stereoisomer. They having different arrangement of atoms or group around the chiral center. Now here first and second, that stereoisomer contain a chiral carbon. They contain a chiral carbon, and also there is no any element of symmetry. In first and second, they contain chiral carbon. There is no element of symmetry. त्यामध्ये element of symmetry का नाहीये? तर suppose this is the plane passing through the molecule. Now that plane divides that molecule into 2 equal part. Equal part मध्ये divide करतं, but they are not mirror images of each other. Therefore, there is no plane of symmetry. Similarly, in second also, there is no plane of symmetry, and thus first and second do not having any plane of any element of symmetry. Hence, they are optically active. They are optical isomer. Okay. Now, what's about the relation between first and second? Suppose this is the mirror in between them. त्यामध्ये mirror आहे असं आपण consider करूया. Now, are they mirror images of each other? हे दोन्ही एकमेकाचे mirror images आहेत का? Yes, they are mirror images of each other. Right? Because suppose इथं आपण वरचा OH बघूया. हा फ्रंटला आहे. मिरर मध्ये सुद्धा फ्रंटला दिसतोय. Suppose this OH is on the back side, then here also that OH is on the back side. Means that first and second, they are mirror images of each other. They are mirror images of each other. And suppose यामधला एक इमेज आपण उचलला आणि दुसऱ्यावरती मॅच करायचा प्रयत्न केला. They do not match with each other. They do not match with each other. Thus, first and second are non-superimposable mirror images of each other. They are non-superimposable mirror images of each other, and thus first and second are optical isomers, and they are non-superimposable mirror images of each other. Hence, they are enantiomers. First and second, they are enantiomers, out of which one should be dextro and second should be Leo isomer. What's about the third and fourth? That third and fourth, they are also mirror images of each other. ते सुद्धा एकमेकाचे mirror images आहेत. But that stereoisomer third and stereoisomer fourth, they are not different. Now question arises, why the stereoisomers are same? मी त्याला सेम का म्हटलं? That stereoisomer number 4, या 4 ला आपण काय करूया? त्याला आपण 180 मधून रोटेट करूया, 180 मधून रोटेट करूया. मग रोटेट केल्यानंतर काय होईल बघा, हा जो COOH आहे तो इथं येईल, बरोबर, आणि हा COOH या बाजूला जाईल. त्यानंतर हे OH कुठे जाणार? OH इकडच्या बाजूला येतील दोन्ही, आणि हायड्रोजन या बाजूला येतील. म्हणजे त्याला 180 मधून रोटेट करायचं. रोटेट केल्यानंतर हे COOH खाली जातो, इथला वर जातो. हे जे हायड्रोजन्स आहेत, दोन्ही हायड्रोजन कुठे जाणार आहेत? या बाजूला, आणि OH इकडच्या बाजूला येतील. ठीक आहे, लक्षात आलं? आणि रोटेट 180 मधून केल्यानंतर जे स्ट्रक्चर आहे, इट इज सिमिलर टू थर्ड. That means that two stereoisomers are same. That two stereoisomers are same. Okay, and thus here that tartaric acid exist only 3 stereoisomer. आपण मगाशी फॉर्म्युलाने सांगितलं होतं there are 4 possible stereoisomer and suppose these are the 4 possible stereoisomer, but that third and fourth they are not different. Our tartaric acid having only 3 stereoisomer. Now out of that we have studied relation between first and second. What's about the first and second? They are optical isomers and they are non-superimposable mirror images of each other. Hence, they are enantiomers, out of which one is dextro and second is the Leo isomer. Okay, now let us see about the third one. What's about the third? That third molecule is a achiral molecule and it is optically inactive. Now, question arises, why it is optically inactive? What's about the third? That third having 2 chiral center. Okay, this is the chiral carbon. Here also this is the chiral carbon. Okay, now this third stereoisomer having 2 chiral carbon, but there is a plane of symmetry. There is a, suppose this is the imaginary plane passing through the molecule. This is the imaginary plane passing through the molecule. Okay, now this plane divides that molecule into 2 equal parts. हे प्लेन या मॉलिक्यूलला 2 इक्वल पार्ट मध्ये डिवाइड करतं and that 2 equal parts are mirror images of each other. These are the mirror images of each other, and therefore that stereoisomer third possesses plane of symmetry. Hence it is optically inactive. It do not show optical activity and such molecules are called achiral molecule. अशा molecule आपण काय म्हणतो? Yes, it is called as the achiral molecule. Okay, now लक्षात आलं why it is achiral? Because it having chiral center, but there is a plane of symmetry. Therefore, it is a chiral molecule and it is optically inactive. And that type of form, that form is called mesoform. अशा फॉर्मला किंवा अशा स्टेरिओआयसोमरला आपण मेसोफॉर्म असं म्हणतो. लेट अस सी रिलेशन बिटवीन फर्स्ट अँड थर्ड. व्हॉट्स अबाउट द फर्स्ट अँड थर्ड? आर द मिरर इमेजेस ऑफ इच अदर? They are not mirror images of each other. First and third are not mirror images of each other, and hence that pair is called distereomers. It is called distereomers because they are not mirror images of each other. Similarly, let us see relation between second and third. Relation between second and third. They are also not mirror images of each other. Hence, this is also called a pair of distereomers. Okay, thus there are 2 pairs of distereomers, first and third, second and third, because they are not mirror images of each other. Okay, now our tartaric acid exists in 4 different forms. First one is the D-tartaric acid, that is dextroisomer. Second one is the L-tartaric acid. Third one is the DL tartaric acid, and fourth one is the mesotartaric acid. What is meant by D-tartaric acid? It is dextroisomer of tartaric acid. It can rotate the plane of PPL in a clockwise direction, that is towards the right side. Therefore, it is dextroisomer, and the specific rotation is plus 12 degree. Means it can rotate the plane of PPL by 12 degree towards the right side. Okay. Then second one is the L isomer, that is Leo isomer of tartaric acid. Then it can rotate the plane of PPL towards anti-clockwise direction. We know that. What should be the specific rotation? What should be the alpha? It should be minus 12 degree. It should be minus 12 degree. Means both the form of tartaric acid, they rotate the plane of PPL by the same angle, just towards opposite direction. Therefore, we have shown one by plus sign and second by negative sign. One is the plus 12 degree, second is the minus 12 degree. Okay, while third form is the DL tartaric acid, and it is the racemic mixture with the equimolar mixture of dextro and Leo isomer. That means equimolar mixture of first and second stereoisomer is called DL tartaric acid. It is optically inactive. Now, what should be the alpha? Yes, it should be the 0 degree because it is optically inactive. Therefore, there is no rotation of PPL. Hence, alpha specific rotation should be 0 degree. Okay, this is the third form. Now, let us see last form is the mesotartaric acid. Mesotartaric acid, this form having 2 chiral carbon, but there is a plane of symmetry. Hence, it is optically inactive. It cannot rotate the plane of PPL. It is optically inactive due to internal compensation. And that form is called as the meso form. त्याला आपण मेसो टार्टारिक ऍसिड असं म्हणतो. What's about the specific rotation? It should be 0. Okay, this is just about the optical isomerism in tartaric acid. मग यामध्ये आपण काय स्टडी केलं होतं ऑप्टिकल आयसोमेरिझम मध्ये? First, is it having chiral carbon? Yes, that molecule having 2 chiral carbon. Therefore, according to formula 2n, there are 4 possible stereoisomer. आपण तेही दाखवले. त्यामधलं रिलेशन्स आपण स्टडी करत असताना आपण थर्ड आणि फोर्थ हे जे दोन आयसोमर्स आहेत त्यामध्ये आपण काय सांगितलं होतं? थर्ड आणि फोर्थ that isomers are same because suppose one is rotated by an angle 180 degree, we get the another. Therefore, that two isomers are not different. पण ते सेम आहे. And thus tartaric acid having only 3 stereoisomer. मग ते 3 stereoisomer तुमच्या समोर आहेत. त्यामधलं रिलेशन आपण सांगितलं. What is the relation between first and second? They are optically active because there is a chiral carbon. There is no any element of symmetry. Hence, they are optically active. First and second. And they are non-superimposable mirror images of each other. And thus, first and second are enantiomers. One is dextro and second is the Lewis isomer. But what's about the third? It having chiral carbon, but there is an element of symmetry and therefore it is optically inactive.